we're going to consider an ideal pendulum for now, which is a pendulum where we're going to neglect the weight of the string and consider the object attached to the string as a point particle. So we're going to neglect its shape. Later on, we're going to put back the mass of the string, and we're going to add various shapes to our pendulum as we're going to introduce rotational dynamics. So let's look at the baby case, ideal pendulum. They told us that we have an object of 2 kilograms attached to that pendulum, and they gave us the length of the string. So here's the pendulum. Again, we're considering the object as a zero-dimensional point, so L is from where the string is attached to the center of mass of the object. The mass is entirely on the object attached to the string. And they're telling us that we're going to displace this pendulum by an angle of 30 degrees with respect to the vertical. And we're going to release it from rest. Obviously, as we do this, we know that as we're going to release it, the pendulum is going to oscillate, reach another extremity, and then bounce back and forth. What the question is asking is to figure out the velocity at the lowest position as it swings back and forth. So obviously on the first swing, the velocity will be towards the left. Then as going to come back, then the velocity will be towards the right, etc., etc. So this is a typical example of how we can see the potential energy initially that will be converted into kinetic entirely at its lowest position, then back to potential, then back to kinetic, etc., etc., etc. So let's give points to, let's say, the lowest position. Let's call it A. That's the point at which we're interested about or concerning the velocity. Since we know something about the beginning, we know we start from rest, we know that keyword is going to tell us something about the kinetic energy, then let's pick this point and let's call it B. So those are going to be the 2 points that we're going to consider. In this case, the only system that we're worried about is the pendulum. That's the massive system. So that means we're going to have to add a set of energy, kinetic and potential, for that particular massive object. And the next step is to identify the datum or a coordinate system. Specifically, where are we going to put the x-axis, which will allow us to measure all the vertical position. So far, the way that we chose our coordinate system, remember, we either consider the initial point, B, or we consider the final point, A. Here's a case where we're going to pick a different point. Now, I would strongly suggest that you redo this problem by picking the origin at B, and then you redo this problem by picking the origin at A, just so that you get to practice pendulums more and more. Because again, those systems are going to come back, and they're going to come back with an increasing complexity. What I'm going to do is I'm going to pick the location of my coordinate system at point C. And even though you may be thinking right now, why? You will understand that as you redo this problem and select B and select A. In addition, point C will be the only point allowed as we're going to revisit this problem in chapter 10 and 11 and redo a similar analysis. So just so that we get the good habits, remember, every time you're going to be facing with a pendulum, pick the origin of your coordinate system at the axis of rotation. So in this case, I'm going to pick a coordinate system at point C. And again, remember, as we do energy, we always have to pick the positive y vertically and up. Okay? Questions so far? Mallory, are you okay? Seems like you were trying to stop your video. I hope I did it for you without messing you up. Oh, I had questions in ECW5. Okay, I will get back to your question, Honoka, right after this problem. And same for Ray. Sorry, I wasn't watching that screen. Okay, so let's get started. We write the energy equation. As usual, we're going to have the sum of the work term plus we only have one massive system, therefore only one set of energy. One kinetic, one potential due to gravity, one potential due to spring. In this case, obviously, we don't have any spring, so we can skip the potential due to the spring. So we only have kinetic and potential due to gravity. Duplicate both terms on the other side. I chose my first state to be state B and my second state to be state A. And again, you can call them whatever you want, 1, 2, A, B, whatever. Okay. So this is our usual starting point. Let's focus right away on the work term. And for us to identify how many work terms do we have, all we have to do is do a quick free body diagram between those two states. Let's say right here. So as the pendulum is in this particular state between B and A, what are the forces acting on this little ball, which is our system? Let's review Newton. What are the external forces acting on this particular? Yeah, excellent. The weight as usual. Anything else? And of course the tension. Good. So technically, since we have identified two forces, we should have two work terms. But remember, as we go through the list, we realize and remember that since we use PEG in our equation, we don't have to introduce the work done by the weight. It's either or. So really, we only have to consider the work done by the tension. Therefore, this is only work done by tension, which is the integral of vector t dot dr. As usual, let's plot t and dr and look at the relationship between the two so that we can calculate the dot product. That's my trajectory. Therefore, dr is tangential. Based on the fact that dr is obviously a vector that is tangential to the path, what is the clear relationship between the vector dr and the force t at any point on that path as he oscillates in the circle? Yeah, excellent. And therefore, since t is perpendicular to dr, we know by the property of the dot product that this is 0. Bang! Hence, no work. Excellent. Good. Now let's look at every term. Let's put the functional form of each. And go through each term and ask yourselves whether this term is 0 or not. So, first term, kinetic term. At position B, do we have a velocity or not? Therefore, do we need to keep this term or not? Excellent. The key word here, thank you, John, is we start from rest. Therefore, rest implies that we have no velocity. Therefore, VB is 0. Therefore, this term is 0. Next one, MGHB. When we are at position B, are we located on the x-axis that we've chosen? Nope. Therefore, we're going to have to keep this term. So now the next step is let's try to figure out what HB is. Obviously, B is below the x-axis. Therefore, we expect it to be negative. And remember, we are after the vertical position of our system at B. So based on geometry, could you tell me the value of HB? Which in green will be this one. vector that starts at X and ends where B is. Here, we're going to have to identify a right angle triangle. Yeah, excellent, Tyson. It will be nothing less but the length, this is L, times cosine alpha. Perfect. And it will be negative L cosine alpha. Therefore, the left term will be negative mgh L cosine alpha. Perfect. Perfect, perfect. Next one. VA. Is our object moving at state A? Yep, obviously it's moving because that's what we're looking for. So let's keep that one. Since we've nuked the other V, feel free to drop the subscript if you want to. That's up to you whether you want to keep it or not. At HA, are we, or at state A, are we on our x-axis? Now I'm looking at the last term. Nope, we're not on the x either. So that means we can have a term here. Similarly, state A is below the x-axis, so we know it's going to be negative. Again, by geometry, could you give me the functional form of HA, which is the vertical distance of state A as measured from the x-axis? Remember, the pendulum oscillates, and the length of the pendulum represents the radius, doesn't change. Excellent. Negative L. Perfect. And again, negative, because we're below the x-axis. That's it. Perfect. Therefore, the last term will be negative mgl. And that's it. Now we can solve for V. Obviously, I can nuke the velocity. And V will be, I can move this term on the other side, and I can factor GL out. GL 1 minus cosine alpha square root, and that would be in meters per second. I know G, 9.81, positive. I know L, whatever that was, 5 meters. I know alpha, 30 degrees. I'm good to go. I don't even care about the mass. Okay? Questions? Yes, Ray, you can and you should. As I mentioned earlier, I would strongly suggest that you redo this problem by taking the x-axis at point A and then redo it at point B. And then I hope that you're going to appreciate the pain that you're going to have to go through to figure out the potential energy to the gravity term. And then compare it with this choice of picking it at C. But yes, please do it. Whenever you do energy problem, when you practice, always redo the same problems several times by picking a different coordinate system and see how the potential energy term to gravity changes. It's always good practice. Good. Any other questions?